What if I told you that everything you see around you, every star in the night sky, every galaxy spinning through the cosmos, what if all of it exists not in 3 dimensions, but as information encoded on a 2-dimensional surface at the edge of the universe? What if our reality is a hologram, a cosmic projection where depth itself is an illusion? Scientists studying black holes have discovered evidence suggesting our entire universe might be written in a cosmic code, on a distant boundary we can never reach. Tonight, we journey through evidence that challenges everything we thought we knew about the nature of reality itself. Before we begin, please like and subscribe to our channel, and let us know in the comments below where in the world you're watching from. Prepare yourselves. We begin. In 1974, a young physicist named Stephen Hawking made a calculation that would haunt theoretical physics for the next 5 decades. Working in his Cambridge office, Hawking applied the principles of quantum mechanics to black holes, those cosmic monsters where gravity becomes so intense that not even light can escape. What he discovered shouldn't have been possible. Black holes, Hawking calculated, slowly evaporate. They emit radiation, now called Hawking radiation, and over unimaginable stretches of time, they shrink and eventually disappear entirely. But here's the problem, the paradox that would launch 1,000 papers and reshape our understanding of reality. When a black hole evaporates completely, where does all the information about everything it ever consumed go? Think about what falls into a black hole. Stars, planets, perhaps entire solar systems. Every atom carries information, the precise quantum state of every particle, the exact configuration of every molecule, the complete history encoded in the structure of matter itself. In our universe, information cannot be destroyed. This principle, information conservation, is as fundamental to physics as the conservation of energy. It's written into the very laws of quantum mechanics. Yet Hawking's mathematics suggested that when a black hole evaporates completely, all that information vanishes, gone, erased from existence. It was as if you burned a book and the ashes somehow contained less information than the pages, not just scrambled information, but genuinely lost information, deleted from the universe forever. This became known as the black hole information paradox, and it represented a direct conflict between quantum mechanics and general relativity, the 2 pillars of modern physics. One of them had to be wrong, or our understanding of reality itself needed a radical revision. For 2 decades, physicists wrestled with Hawking's paradox. Conferences were held, papers were published, arguments raged. The stakes were existential. If information could truly be destroyed, the entire framework of quantum mechanics would collapse. But if information survived somehow, then black holes had to work in ways we'd never imagined. In 1993, a Dutch physicist named Gerard 'Tulft proposed something extraordinary. Working with Leonard Susskind at Stanford, 'Tulft suggested that the paradox revealed something profound about the nature of space itself. The information that falls into a black hole, they argued, doesn't actually disappear into the 3-dimensional interior. Instead, it's encoded on the black hole's two-dimensional surface, its event horizon. Imagine a sphere surrounding a black hole, the boundary beyond which nothing can escape. Tulft and Susskind proposed that everything inside this sphere could be completely described by information written on its surface. It was as if the three-dimensional interior was redundant, a projection from a two-dimensional screen. They called this the holographic principle, named after holograms, those flat images that contain all the information needed to reconstruct a three-dimensional scene. Just as a hologram on a credit card appears three-dimensional despite being encoded on a flat surface, perhaps the entire interior of a black hole was a three-dimensional illusion projected from its two-dimensional boundary. But Tulft and Susskind went further. If the holographic principle worked for black holes, they reasoned, it might work for the entire universe. Perhaps all of reality, everything we experience as three-dimensional space, is actually information encoded on a distant two-dimensional surface. The implications were staggering. The depth you perceive, the distance between objects, the solid three-dimensionality of the world around you, all of it might be a cosmic projection, a holographic illusion emerging from information written in a code we're only beginning to decipher. To understand how radical this idea truly is, we need to explore what it means for information to be encoded on a surface. In our everyday experience, information scales with volume. A larger hard drive stores more data than a smaller one. A library with more shelf space holds more books. We instinctively think of information as something that fills three-dimensional space. But black holes don't work this way. In 1972, physicist Jacob Bekenstein discovered something peculiar. He calculated that the entropy of a black hole, essentially the amount of information it contains, is proportional not to its volume, but to the surface area of its event horizon. Double the radius of a black hole, and you quadruple its surface area, but increase its volume eightfold. Yet the information storage capacity only quadruples, not eightfold. This was deeply strange. It suggested that despite appearing as a three-dimensional object with tremendous volume, a black hole's information capacity was determined entirely by its two-dimensional surface. It was as if the interior didn't really count, as if the volume was somehow less fundamental than the area surrounding it. Bekenstein's discovery established what's now called the Bekenstein bound, a fundamental limit on how much information can be stored in any region of space. Take any spherical region, a room, a planet, or a galaxy. Draw an imaginary boundary around it. According to the Bekenstein bound, the maximum amount of information that region can contain is determined not by its volume, but by the surface area of that boundary. The bound is remarkably specific, approximately 1.4 times 10 to the 69 bits of information per square meter. That's an enormous number, a 1 followed by 69 zeros. But the key point is that it depends on area, not volume. This suggests that at the most fundamental level, the universe organizes information on surfaces, not in volumes. When T. Hooft and Susskind proposed the holographic principle, they were taking Bekenstein's discovery to its logical conclusion. If information is bounded by area, perhaps it's actually stored on area. Perhaps what we perceive as three-dimensional space is an emergent phenomenon, something that arises from information fundamentally encoded on two-dimensional surfaces. The holographic principle might have remained an elegant speculation, A curious idea about black holes, if not for a remarkable discovery in string theory. In 1997, Juan Maldacena, a young physicist at Harvard, found something that would earn him citations from thousands of papers and transform theoretical physics. Maldacena was working with string theory, the ambitious framework that attempts to unify quantum mechanics and gravity by proposing that fundamental particles are actually tiny vibrating strings. String theory requires extra dimensions beyond the 3 spatial dimensions we experience, typically 6 or 7 additional dimensions curled up so small we can't perceive them. What Maldacena discovered was a precise mathematical relationship between 2 seemingly different theories. On one side was a theory of gravity in a special curved spacetime called anti-de Sitter space, or ADS, a universe with negative curvature, like a saddle shape extended throughout all of space. This theory existed in 5 dimensions, 4 spatial dimensions plus time. On the other side was a theory with no gravity at all, living on the 4-dimensional boundary of this 5-dimensional space. This boundary theory described quantum fields, the fundamental entities of particle physics, but contained no gravitational force whatsoever. Maldacena proved these 2 theories were exactly equivalent. Every event in the 5-dimensional gravitational universe corresponded precisely to an event in the 4-dimensional boundary theory. The interior spacetime, with all its gravitational dynamics, could be completely described by physics happening on its lower dimensional boundary. The bulk, as physicists call the interior, was holographically encoded on the boundary. This is called the ADS/CFT correspondence, anti-de Sitter space/conformal field theory correspondence, and it remains one of the most important discoveries in theoretical physics. For the first time, physicists had a concrete, mathematically rigorous example of the holographic principle in action. Gravity in one description became quantum fields in another. 3-dimensional space emerged from 2-dimensional information. The technical details are complex, but the essential point is revolutionary. Maldacena provided proof of concept. The holographic principle wasn't just philosophical speculation, it was mathematically real, demonstrable, and precise. Space itself could emerge from information encoded on lower dimensional surfaces. Maldacena's ADS-CFT correspondence works in a universe with negative curvature, not the flat or slightly positively curved universe we actually inhabit. Our universe isn't anti-de Sitter space. It's expanding, filled with dark energy, and doesn't have the properties that make the mathematical proof so elegant. This gap between theory and reality has challenged physicists for decades. But in recent years, theorists have made remarkable progress extending holographic ideas to more realistic cosmological models. The key insight is that if the holographic principle is truly fundamental, if it reflects something deep about how information and space relate, then it should apply to all universes, not just the special mathematical case Maldacena solved. Several research groups have developed holographic descriptions of universes that expand, contain matter and energy, and exhibit properties much closer to our own. These models suggest that even our real physical universe might have a holographic description, with all the physics we observe emerging from information encoded on a distant cosmic boundary. This boundary isn't somewhere you could travel to. It's not a physical wall at the edge of space. Instead, it's a theoretical construct, a mathematical surface where the holographic encoding lives. Think of it as the cosmic screen from which our three-dimensional reality is projected, though projected is itself a metaphor for a mathematical relationship that transcends simple visualizations. In these holographic universe models, the cosmic screen exists in the infinite future or at infinite distance, depending on the formulation. It's the ultimate boundary of space-time itself. And encoded on this boundary, according to the holographic principle, is all the information about everything that happens everywhere in our three-dimensional cosmos. You, sitting there right now, reading or listening to these words, from a holographic perspective, you're fundamentally information encoded on this distant boundary. Your thoughts, memories, and experiences, the particles that compose your body, the atoms and molecules and cells, all of it described completely by data written on a cosmic surface you'll never touch. This isn't mysticism or science fiction. It's the logical consequence of taking the holographic principle seriously and applying it to cosmology. And as strange as it sounds, this perspective has proven remarkably productive, generating new insights into quantum gravity, the early universe, and the fundamental nature of space-time. But here's what keeps physicists awake at night, staring at equations and wondering about the nature of existence. If the holographic principle is true, which description is more fundamental? Are we truly three-dimensional beings, with the holographic encoding on a distant boundary merely an alternative mathematical description? Or are we actually the boundary information, with three-dimensional experience emerging as a kind of illusion, a convenient way for the universe to organize and process data? Think about that hologram on your credit card again. When you look at it, you see depth that isn't really there. The image appears three-dimensional, but it's actually flat. All the information creating that three-dimensional appearance is encoded in microscopic patterns on a two-dimensional surface. Is our universe the same? Do we experience three dimensions not because we exist in three dimensions, but because that's how two-dimensional information processes itself? Some physicists argue that both descriptions are equally real, equally fundamental, that asking which is more true is like asking whether a novel is more real than the story it tells. The mathematics and the experience are two aspects of the same reality. But others suggest the holographic description might be more fundamental precisely because it resolves paradoxes like Hawking's information problem. If information is fundamentally two-dimensional, encoded on surfaces, then it can never truly disappear into black holes, because the black hole itself is just another holographic projection. The information was always on the boundary, always preserved, never actually inside the black hole's interior. This is where the evidence forces us to confront an uncomfortable possibility, that our experience of three-dimensional space, of depth and distance and solidity, might be the universe's user interface, not its source code. That reality's true structure exists in a lower dimension, and we are patterns of information experiencing ourselves as something more than we fundamentally are. But the evidence for this extraordinary claim extends beyond theoretical speculation. Multiple independent discoveries across different fields of physics point toward the same conclusion, building a case that becomes harder to dismiss with each new revelation. The first concrete evidence for holographic reality comes from black holes themselves, those cosmic laboratories where gravity becomes so extreme that space and time exchange roles. In 2004, Samir Mathur at Ohio State University made a calculation that changed how physicists think about what's inside a black hole's event horizon. Mathur worked with string theory to model what happens when matter collapses to form a black hole. The conventional picture imagined matter crushing down to a point singularity at the center, with empty space between the singularity and the event horizon. But Mathur's calculations showed something radically different. The interior, he found, wasn't empty at all. Instead, it was filled with what he called a fuzzball, a dense tangle of strings that extends throughout the entire volume inside the event horizon. Here's what makes this remarkable. The fuzzball's structure is entirely determined by information on the event horizon surface. The three-dimensional interior configuration emerges from two-dimensional boundary data. It's not that the interior is somehow less real, but that it's redundant, completely specified by surface information. In 2012, researchers at the Institute for Advanced Study calculated how Hawking radiation escapes from black holes. They found that the radiation doesn't actually emerge from inside the event horizon at all. Instead, it's produced by quantum processes right at the surface. The event horizon itself acts like a hot membrane, radiating particles from its two-dimensional structure. The three-dimensional interior plays no direct role in the evaporation process. More remarkably, in 2016, a team led by Ahmed Al-Hariri established what they called the firewall paradox. Their calculations suggested that anyone falling into a black hole would encounter a wall of high-energy particles right at the event horizon, a prediction that seemed to contradict general relativity's requirement that nothing special happens at the horizon for a falling observer. The paradox is resolved in holographic models, where the event horizon isn't a simple surface, but rather the fundamental reality, with the interior being an emergent description. These findings aren't isolated quirks of black hole physics. They're telling us something profound. In the most extreme gravitational environments we know, nature behaves holographically. Three-dimensional space emerges from two-dimensional information. In 2013, the European Space Agency's Planck satellite released the most precise map ever made of the cosmic microwave background, the afterglow of the Big Bang, radiation that has traveled through space for 13.8 billion years, carrying information about the universe's earliest moments. Scientists expected the temperature fluctuations in this ancient light to follow specific statistical patterns predicted by our best cosmological models. And mostly they did. The universe looked exactly as the standard model of cosmology said it should. But there were anomalies, subtle deviations from predictions that have puzzled cosmologists for 2 decades now. One anomaly stands out: the cold spot. It's a region about 1.8 billion light-years across where the cosmic microwave background is slightly cooler than the surrounding areas, about 70 microkelvins colder to be precise. That might not sound significant, but in the nearly uniform cosmic microwave background, it's enormous. Statistical analyses suggest this cold spot should occur by random chance in less than 2% of universes like ours. Conventional explanations have struggled to account for it. Some researchers proposed it might be a cosmic void, an unusually empty region of space between us and the cosmic microwave background. But observations of galaxies in that direction found nothing unusual. The void hypothesis failed. In 2017, researchers at the University of Waterloo proposed something different. The cold spot might be a signature of holographic physics. In their models, quantum fluctuations in the early universe don't just produce ordinary density variations, they also produce holographic anomalies, regions where the relationship between the three-dimensional bulk and the two-dimensional boundary becomes momentarily distorted. These distortions would appear in the cosmic microwave background as temperature anomalies with specific statistical properties. When the Waterloo team analyzed the cold spot using this holographic framework, they found patterns consistent with their predictions. The cold spot's unusual characteristics, its size, shape, and statistical improbability, matched what holographic models would generate far better than conventional explanations. This doesn't prove the universe is holographic. The evidence isn't that definitive, but it represents something significant, an observable signature in the actual cosmos that aligns with holographic predictions. The cold spot might be our first glimpse of the holographic nature of reality written in the universe's oldest light. Perhaps the most mind-bending evidence comes from recent discoveries about quantum entanglement, that strange phenomenon where particles separated by vast distances remain connected, their properties correlated in ways that seem to transcend space itself. Einstein called it spooky action at a distance and never fully accepted it. But experiments have confirmed it repeatedly. Entanglement is real. In 2013, physicists Mark van Ramsdonk and Brian Swingle independently made a breakthrough discovery. Quantum entanglement and space-time geometry are intimately related. Using ADS-CFT correspondence, Van Ramsdonk showed that the connectivity of space, the fact that different regions of space relate to each other in smooth, continuous ways, emerges from entanglement between quantum particles. The mathematics was explicit and stunning. Take a region of spacetime in the gravitational bulk theory. Remove all quantum entanglement from the corresponding region in the holographic boundary theory. The spacetime region tears apart. The geometry itself ceases to exist. Space, Van Ramsdonk proved, is held together by quantum entanglement. This led to a radical proposal. Spacetime itself might be an emergent phenomenon, something that arises from more fundamental quantum information, particularly the patterns of entanglement connecting different parts of that information. We don't exist in space, we exist in quantum information, and what we call space is how that information organizes itself. In 2015, Leonard Susskind and Juan Maldacena extended this further with their ER equals EPR conjecture. ER refers to Einstein-Rosen bridges, wormholes, theoretical tunnels through spacetime. EPR refers to Einstein-Podolsky-Rosen entanglement, the quantum connection between particles. Susskind and Maldacena proposed these are the same thing, viewed from different perspectives. When two particles are entangled, they suggested, they're connected by a quantum wormhole, a geometric bridge through spacetime that exists at scales far too small to observe directly, but that nevertheless provides the underlying mechanism for quantum correlations. Entanglement isn't action at a distance, it's connection through quantum geometry. The implications cascade outward. If entanglement creates spacetime geometry, and if our universe is holographic, then the three-dimensional space we experience emerges from patterns of entanglement in the two-dimensional holographic boundary. We live inside a vast quantum network, where the connections between information create the illusion of distance and separation. Experiments testing these ideas are ongoing. In 2019, researchers at the University of Colorado created artificial quantum systems that exhibit holographic behavior, showing emergent spatial dimensions arising from patterns of entanglement. These aren't full universes, just quantum simulators with dozens of particles, but they prove the concept works, entangle quantum information the right way, and spatial dimensions appear where none existed before. There's another striking piece of evidence, this one from information theory itself. In 2018, theoretical physicists Raphael Bousso and Netta Engelhardt calculated something called the covariant entropy bound. Essentially, the maximum rate at which information can pass through any surface in spacetime. Their calculations revealed something peculiar. The universe appears to have a maximum bandwidth, a fundamental limit on information transfer that depends on surface area, not volume. Imagine a sphere surrounding any region of space. According to Bousso and Engelhardt, the rate at which information can pass through that spherical surface is limited by the surface area of the sphere, measured in Planck units, the smallest meaningful units of length in physics. This bandwidth limit shows up everywhere. It constrains how fast information can travel between quantum systems. It limits the rate at which black holes can consume information. It even bounds how quickly the universe itself can process information as it evolves forward in time. Why would the universe have an area-dependent bandwidth limit if reality were fundamentally three-dimensional? In 3 dimensions, you'd expect limits based on volume. A larger region should be able to process more information simply because it contains more space. But the covariant entropy bound says otherwise. Nature imposes limits based on surfaces, not volumes, suggesting that at the deepest level, information lives on surfaces. This represents just one piece of a much larger puzzle, emerging from decades of careful theoretical work and astronomical observation. The evidence points consistently in one direction. Our three-dimensional universe exhibits properties that make sense if it's holographic, if space itself emerges from information encoded on lower dimensional boundaries. But the truly strange implications are only beginning to reveal themselves. If we take the holographic principle seriously, we can calculate the resolution of the cosmic hologram, how finely information is encoded on the boundary that projects our reality. The calculation involves fundamental constants. The Planck length, about 1.6 times 10 to the minus 35 meters, represents the smallest meaningful distance in physics. At this scale, quantum effects and gravity become equally important, and space-time itself becomes uncertain, fluctuating wildly. The cosmic hologram's resolution is approximately 1 bit of information per Planck area, a square with sides 1 Planck length long. This is staggeringly fine-grained. To put it in perspective, consider a sphere 1 meter in radius surrounding you. The surface area of that sphere is about 12.6 square meters. How many Planck areas fit on that surface? Approximately 10 to the 70. That's a 1 followed by 70 zeros, 100 billion, 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 billion pixels. Now scale up to cosmic dimensions. The observable universe extends about 46 billion light-years in every direction. If we imagine a spherical boundary surrounding all of observable space, the surface area is approximately 10 to the 123 square meters. The number of Planck area pixels on this cosmic screen is therefore around 10 to the 193, a number so vast that there's no familiar comparison. Every atom in the observable universe, all 10 to the 80 of them, represents less than a trillionth of a trillionth of a trillionth of a percent of the cosmic hologram's information capacity. This tells us something profound. If our universe is holographic, the encoding is incomprehensibly detailed. Every quantum state, every particle interaction, every thought and memory and physical process, all of it encoded with a resolution that makes even our finest human technologies look like crude stone tools by comparison. But here's what's remarkable. Despite this vast information capacity, it's still finite. The universe, from a holographic perspective, is processing a huge but limited amount of information. And this finitude has consequences. It suggests there's a limit to how complex reality can become, a maximum resolution to the simulation, if we can even call it that we inhabit. The most disturbing evidence comes from recent work on the emergence of time itself. We've been discussing how space emerges from holographic information, but what about time? Time seems even more fundamental than space, the one dimension we can't avoid moving through, the axis along which cause and effect unfold. In 2016, physicist Sean Carroll at Caltech published calculations suggesting time, like space, might be emergent from something more fundamental. Working within holographic frameworks, Carroll showed that the arrow of time, the fact that time flows forward, that entropy increases, that the past differs fundamentally from the future, arises from how information is organized on the holographic boundary. The key insight involves entropy, the measure of disorder in a system. The second law of thermodynamics says entropy always increases. A broken cup doesn't spontaneously reassemble. Heat flows from hot to cold, never the reverse. This gives time its direction, its arrow pointing from past to future. But why does entropy increase? In standard physics, it's a statistical accident. Systems have vastly more disordered states than ordered states, so random fluctuations tend toward disorder simply because disorder is more probable. But this explanation has always been somewhat unsatisfactory. Why should the universe start in a low entropy state in the first place? Holographic cosmology offers a different answer. If the universe is encoded on a two-dimensional boundary, then what we call time is the evolution of that encoding, the sequence of states the holographic information passes through. The arrow of time points in the direction of increasing entanglement complexity on the boundary. As the universe evolves, quantum systems become more entangled, creating more complex patterns of correlation. This increasing entanglement complexity is what we experience as time's forward flow. In 2019, researchers at the University of British Columbia ran computer simulations of holographic universes. They encoded quantum information on a boundary and let it evolve according to quantum mechanical rules. Emergent spacetime appeared in their simulations, along with an arrow of time. The simulated universes evolved from simple, low entanglement states toward complex, highly entangled states. Observers within these simulated universes would experience this evolution as the forward flow of time. The implications are staggering. Time might not be a fundamental feature of reality, but rather something that emerges from how quantum information processes itself. At the holographic boundary, there might be no time at all, just timeless patterns of information. Time exists only in the emergent bulk, in the holographic projection we call our three-dimensional universe. This means that from the perspective of the holographic boundary, all of history, past, present, and future, might exist simultaneously encoded in a static pattern of information. What we experience as temporal flow would be an artifact of how we, as patterns within the hologram, process information. We move through time not because time flows, but because the holographic encoding includes temporal structure as part of its data. The most remarkable discovery involves the relationship between observation and reality in holographic cosmology. Quantum mechanics has always had a measurement problem. Particles exist in superposition, occupying multiple states simultaneously until they're observed, at which point they collapse into definite states. But what counts as observation? What causes collapse? The role of consciousness has haunted quantum mechanics since its inception. Holographic cosmology might offer an answer, though it's not necessarily a comfortable one. In 2018, physicist Matthew Hedrick at Brandeis University calculated how information propagates in holographic spacetimes. He found something unexpected: the emergence of observers. Localized systems capable of processing information is not an accident, but a necessary feature of holographic universes. Here's why. For a holographic universe to exist, information on the boundary must be processed, must evolve, must organize itself into increasingly complex patterns. This processing requires what information theorists call decoherence, the mechanism by which quantum superpositions break down into classical, definite states. And decoherence requires observers. But in holographic models, observers don't cause decoherence from outside the system. Rather, observers are patterns within the holographic information that enable the information to process itself. Consciousness, in this view, is what allows the holographic boundary to explore its own state space, to determine which of many possible quantum states become actualized in the emergent bulk spacetime. This suggests a strange kind of participatory universe, where consciousness isn't separate from physical reality, but integral to how reality manifests. The hologram needs observers to compute itself, to determine what exists in three-dimensional space based on the information encoded in 2 dimensions. Several research groups have explored this idea through the lens of integrated information framework, a framework for understanding consciousness developed by neuroscientist Giulio Tononi. In 2020, physicist Nima Arkani-Hamed at the Institute for Advanced Study showed that integrated information, the kind of information processing that creates conscious experience, naturally emerges in holographic spacetimes with sufficient complexity. Arkani-Hamed's calculations suggest that consciousness isn't just compatible with holographic cosmology, it's almost inevitable. Once a holographic universe reaches a certain threshold of complexity, integrated information processing appears. Observers emerge, not as special additions to reality, but as necessary features of how holographic information organizes itself. This doesn't mean the universe is conscious in any human sense, but it does suggest that observer-like information processing is built into the fabric of holographic reality, that the distinction between physical processes and observational processes might be less clear than we've assumed. All of this points toward a conclusion that would have seemed like science fiction just decades ago. Reality, at its most fundamental level, might be discrete rather than continuous. The holographic principle, with its Planck scale resolution, suggests the universe isn't made of infinitely divisible stuff, but rather of finite bits of information. In 2019, physicist Chiara Marletto at Oxford University formalized what she calls constructor theory, a new way of thinking about physics based not on laws that govern how states evolve, but on which transformations of information are possible or impossible. Working within this framework, Marletto showed that many physical laws, including conservation principles and the second law of thermodynamics, can be derived from constraints on information processing. This suggests physics is fundamentally about information, not about matter and energy. Matter and energy are ways information manifests in emergent spacetime, but the bedrock reality is the information itself. And if information is fundamental, then reality is, in some sense, computational, Not a computer simulation created by some external programmer, but a self-organizing system of information processing its own existence. The evidence extends beyond the realm of theoretical physics into the structure of physical laws themselves. Why do particles come in discrete types? Electrons, quarks, neutrinos. Why are their properties quantized, existing only in specific values rather than any arbitrary value? Holographic cosmology suggests these discrete features reflect the digital nature of information on the cosmic boundary. Particles are types of information patterns, and they're quantized because information itself comes in discrete bits. Recent work on quantum error correction has revealed something even stranger. In 2015, physicist Daniel Harlow at MIT showed that the bulk spacetime in ADS-CFT correspondence behaves exactly like a quantum error-correcting code. The holographic boundary encodes information redundantly, and the emergent spacetime has built-in mechanisms to protect that information from corruption. This is precisely how quantum computers work. They encode information in ways that allow errors to be detected and corrected. The universe, it seems, operates on similar principles. The holographic boundary is a cosmic quantum computer, and spacetime is the error-corrected output of that computation. The evidence extends beyond theory into practical observations. The discrete nature of quantum mechanics, the finite information content of black holes, the area-dependent entropy bounds, the maximum bandwidth of information transfer. All of these empirical facts align with a holographic, informational picture of reality. The universe behaves as if it's processing a vast but finite amount of information, according to rules that preserve and protect that information even as it evolves and becomes more complex. What scientists found in studying black holes half a century ago has led inexorably to a new understanding of existence itself. Reality is information. Space and time are emergent, and we are patterns within a cosmic hologram of incomprehensible complexity and breathtaking elegance. The most profound implications emerge when we consider what this means, not just for physics, but for existence itself, for consciousness and meaning, and the nature of what it means to be real. To truly understand what physicists mean when they say the universe is holographic, we need to explore the mathematical machinery that makes this possible. At its heart, the holographic principle relies on something called gauge-gravity duality, a profound equivalence between theories that seem completely different on the surface. Imagine two descriptions of reality. In the first description, we have a theory of gravity in a curved spacetime. This is the bulk description, the three-dimensional plus time universe we seem to inhabit. Massive objects curve spacetime, light follows geodesics, black holes form, and all the phenomena of general relativity play out. In the second description, we have a completely different theory living on the boundary of this spacetime, typically one dimension lower. This boundary theory has no gravity at all. It's a quantum field theory, describing the behavior of particles and forces, but operating in a flat spacetime without any curvature. Particles interact through quantum forces, electromagnetic, strong nuclear, weak nuclear, but not through gravity. Gauge-gravity duality says these two descriptions are exactly equivalent. Every event in the gravitational bulk corresponds to an event in the non-gravitational boundary theory. Every black hole in the bulk corresponds to a particular configuration of quantum fields on the boundary. Every gravitational wave propagating through spacetime corresponds to correlations between quantum fields. The mathematics involved is formidably complex. It involves quantum field theory, differential geometry, string theory, and advanced algebra. But the core insight is simple. Gravity in more dimensions equals quantum physics in fewer dimensions. Three-dimensional space emerges from two-dimensional quantum information. One Maldasena's original ADS-CFT correspondence provided the first concrete example. Anti-de Sitter space with a negative cosmological constant corresponds to a conformal field theory on its boundary. The word conformal means the theory has a special symmetry. It looks the same at all scales, like a fractal. This conformal symmetry on the boundary translates into the special geometric properties of ADS space in the bulk. Since 1997, physicists have calculated thousands of examples. Every black hole state in the bulk corresponds to a specific quantum state in the boundary theory. Every collision between particles in the bulk corresponds to scattering amplitudes in boundary quantum fields. Every measurement in the bulk has a boundary equivalent. The correspondence is exact, complete, and mathematically rigorous. But Maldasena's ADS-CFT is just one example, albeit the most thoroughly studied. Physicists have since discovered gauge gravity dualities for other types of spacetimes. In 2011, researchers found holographic descriptions for de Sitter space, universes with positive curvature and accelerated expansion, more like our actual cosmos. In 2015, progress was made on flat spacetime holography, bringing holographic principles even closer to our observed universe. Each of these dualities reveals the same underlying truth. Spacetime geometry emerges from quantum information. The bulk is holographic projection. The boundary is fundamental reality. Or perhaps it's more accurate to say they're equally real, equally fundamental. Two descriptions of the same underlying truth, like how a book and its story are inseparable aspects of the same thing. The holographic principle has gone from fringe speculation to mainstream physics in just 3 decades. Today, it's taught in graduate courses, featured in major research programs, and accepted by most theoretical physicists working on quantum gravity. But acceptance doesn't mean agreement about interpretation or implications. Leonard Susskind, one of the principle's founding fathers, believes holography reveals something deep about information as the fundamental substance of reality. The laws of physics are algorithms, Susskind argues, processing information according to fixed rules. What we call particles, fields, and forces are patterns in that information. Spacetime itself is an output of the computation. Susskind goes further, suggesting our entire universe might be a holographic projection from a boundary we can never observe directly. At conferences and in papers, he's argued that death, the dissolution of the information patterns that constitute a person, might not be final in a holographic universe. If all information is preserved on the boundary as the holographic principle requires, then in some sense, everything that ever happened continues to exist in the complete boundary state. Juan Maldacena takes a more conservative view. ADS-CFT is a mathematical equivalence, he explains. Whether one description is more real than the other is a question beyond physics. What matters is that we've discovered a deep duality, a way to translate between gravitational and quantum mechanical languages. This is a tool for solving problems, understanding black holes, maybe even quantum gravity itself. Yet, even Maldacena acknowledges the philosophical weight of his discovery. In interviews, he's noted that ADS-CFT suggests space-time isn't fundamental, but emergent. We used to think space-time was the stage where physics happened, he says. Now we're realizing space-time is part of the play, something that arises from more fundamental quantum degrees of freedom. Edward Witten at the Institute for Advanced Study, one of the most influential theoretical physicists alive, sees holography as potentially our best path toward understanding quantum gravity, the long-sought theory that unifies quantum mechanics and general relativity. The holographic principle, Witten argues, is telling us that quantum gravity has fewer degrees of freedom than we thought, that it's more constrained, more structured. This is good news. It means the problem is more tractable than we feared. Nima Arkani Hamed goes even further, suggesting that space-time and quantum mechanics themselves might be approximate descriptions of something more fundamental that we haven't yet grasped. Holography is a hint, Arkani Hamed proposes, pointing toward a reformulation of physics that doesn't start with space-time or quantum states, but with something more basic, perhaps some combinatorial structure, some abstract mathematical object that gives rise to both space-time and quantum mechanics as emergent phenomena. Not everyone is convinced. Roger Penrose, whose work on black hole singularities helped earn him the Nobel Prize, remains skeptical of strong interpretations of holography. Mathematics is full of dualities and equivalences, Penrose notes, but this doesn't mean one description is less real than another. Just because we can encode three-dimensional information on a two-dimensional surface doesn't mean the three-dimensional space is illusory. Yet even skeptics acknowledge that holography has proven extraordinarily fruitful. It solved long-standing problems, generated new insights, and opened research directions that continue to produce results. Whether the universe is really holographic, or whether holography is just a powerful mathematical tool, physicists agree it's revealed something profound about how information, gravity, and quantum mechanics relate. The holographic principle forces us to reconsider fundamental assumptions about reality, existence, and our place in the cosmos. If space and time are emergent rather than fundamental, what does that mean for our understanding of existence itself? Consider the question of what's real. In our everyday experience, objects seem real because they're made of matter, they occupy space, they persist through time. But if space itself is emergent, if time is a byproduct of information processing, then what does it mean for something to be real? Is the holographic boundary more real than the emergent bulk? Or is real a category error, a concept that doesn't cleanly apply when discussing the relationship between information and its manifestations? Philosophers working on these questions draw parallels to other cases of emergence. Temperature, for instance, is an emergent property of molecular motion. Individual molecules don't have temperature, they have kinetic energy. Only when you have many molecules do statistical patterns emerge that we call temperature. Yet temperature is perfectly real. You can measure it, feel it, use it to predict behavior. Is space-time like temperature, an emergent property that's real without being fundamental? The holographic principle also raises questions about identity and persistence. If you are fundamentally a pattern of information on the cosmic boundary, then what makes you the same person from moment to moment? In the emergent bulk description, you persist through time as a continuous object. But on the boundary, there's no time, just timeless information patterns. Your entire history from birth to death exists simultaneously as static data on the holographic screen. This touches on ancient philosophical debates about the nature of time and change. The philosopher Parmenides argued that change is impossible, that all of existence is a single, unchanging reality. Holography suggests he might have been onto something. From the boundary perspective, nothing changes. Change exists only in the emergent bulk, in the way three-dimensional observers process temporal sequences from timeless information. There's also the question of free will and determinism. If all of history is encoded on the boundary, is the future already determined? In a sense, yes. The boundary state contains all information about past, present, and future, yet within the bulk, within our lived experience, quantum mechanics remains probabilistic, indeterministic. We experience genuine uncertainty, real choice, even if, from a broader perspective, those choices are already part of the complete boundary encoding. Some philosophers argue this is no different from the block universe view of relativity, where past, present, and future all exist equally in four-dimensional space-time. Holography just adds another layer. The four-dimensional block universe is itself a projection from a lower-dimensional boundary. The implications for free will remain as debatable as ever. Perhaps most profoundly, holography challenges our intuition about fundamentality itself. We tend to think of nature as built from elementary constituents, atoms made of protons, neutrons, and electrons, protons and neutrons made of quarks, quarks perhaps made of strings or other fundamental entities. It's a reductionist picture, where understanding requires finding the smallest pieces. But holography suggests reality might not work this way. Perhaps there are no truly elementary constituents, no bottom layer where reduction ends. Instead, reality might be a web of dualities and equivalences, where different descriptions are useful for different questions, but none is uniquely fundamental. The boundary is fundamental from one perspective, the bulk from another. Neither is more true. Both are necessary to capture the complete picture. This forces us to reconsider fundamental assumptions about the universe, about consciousness, and about whether the questions we're asking even make sense in their traditional formulations. The evidence suggests we might need new categories, new ways of thinking about what exists and how existence relates to information, observation, and experience. The holographic principle, for all its theoretical elegance, faces a crucial challenge. Can it be tested experimentally? Can we find observable signatures that would confirm or refute holographic cosmology? Scientists around the world are pursuing several promising directions. The first involves gravitational wave astronomy. LIGO and Virgo detectors have opened a new window on the universe by detecting ripples in space-time produced by colliding black holes and neutron stars. Future gravitational wave observatories, like the proposed Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will be sensitive enough to detect subtle effects predicted by holographic theories. Specifically, holographic models predict tiny corrections to how gravitational waves propagate through spacetime. These corrections arise because spacetime isn't perfectly continuous at the Planck scale. It has a discrete, pixelated structure inherited from the finite information capacity of the holographic boundary. When gravitational waves with extremely short wavelengths propagate through this discrete spacetime, they should experience slight dispersion, different frequencies traveling at slightly different speeds, like light passing through a prism. The effect is minuscule, far too small for current detectors. But LISA, observing gravitational waves from massive black hole mergers billions of light-years away, might accumulate enough signal to detect Planck-scale dispersion. If observed, it would provide the first direct evidence that spacetime is fundamentally discrete, consistent with holographic predictions. A second experimental avenue involves quantum entanglement. In 2021, researchers at the University of Maryland proposed using quantum computers to simulate holographic spacetimes. The idea is to create quantum systems with carefully engineered entanglement patterns that, according to ADS-CFT, should exhibit emergent spatial geometry. By 2024, small-scale versions of these experiments have been performed using quantum processors with up to 100 qubits. The results are preliminary but encouraging. The quantum systems do exhibit emergent spatial structure consistent with holographic predictions. As quantum computers scale to thousands or millions of qubits over the coming decades, these quantum simulations could provide detailed tests of holographic cosmology. A third approach involves cosmology itself. The Simons Observatory in Chile and the future CMB-S4 experiment will map the cosmic microwave background with unprecedented precision. These observations might detect patterns, specific types of correlations in temperature fluctuations that holographic models predict but standard cosmology doesn't. In particular, holographic cosmology makes specific predictions about non-Gaussianity in the cosmic microwave background, subtle deviations from the purely random patterns expected in conventional models. These non-Gaussian signatures arise from the discrete structure of the holographic boundary and how quantum fluctuations in the early universe couple to this structure. Detecting these signatures would provide strong evidence for holographic cosmology. The European Space Agency is also planning a mission called Theseus, set to launch in the early 2030s, that will study gamma-ray bursts, the most energetic explosions in the universe after the Big Bang itself. Some holographic theories predict that the highest energy photons from distant gamma-ray bursts should arrive slightly delayed compared to lower energy photons, an effect of Planck-scale spacetime structure. Theseus will be sensitive enough to detect these delays if they exist. If the holographic principle is correct, it could enable technologies that seem like science fiction today. Understanding how information fundamentally relates to spacetime might allow us to manipulate spacetime itself in ways currently impossible. Consider quantum computing. Current quantum computers operate on qubits, quantum bits that can exist in superposition of 0 and 1. They're powerful but fragile, easily disrupted by environmental noise. Holographic quantum computing could be fundamentally different. If spacetime is a quantum error-correcting code, as recent research suggests, we might be able to build quantum computers that leverage this natural error correction. The idea is to encode quantum information not in individual qubits, but in patterns that mirror how nature encodes information on holographic boundaries. These holographic quantum computers would automatically correct errors through mechanisms built into their structure, making them vastly more stable and powerful than conventional quantum computers. Several research groups are exploring this possibility. In 2023, researchers at Caltech demonstrated a small-scale holographic quantum memory that stored quantum information with significantly reduced error rates compared to conventional approaches. Scaling this to full quantum computers could revolutionize computing, enabling calculations currently impossible even in principle. Another possibility involves gravity itself. If gravity emerges from patterns of quantum entanglement, as holographic theories suggest, then manipulating entanglement might allow us to influence gravitational fields. This doesn't mean anti-gravity or faster-than-light travel, physics still forbids those, but it might enable more subtle manipulation of space-time curvature, perhaps improving gravitational wave detectors, or even creating microscopic gravitational fields in laboratory settings. The most speculative possibility involves what physicists call ER bridges, traversable wormholes connecting distant regions of space. In 2017, Juan Maldacena, Alexei Malakin, and Fedor Popov showed that in principle, traversable wormholes could be created by carefully manipulating quantum entanglement between two black holes. The energy requirements are enormous, far beyond anything remotely achievable with current or foreseeable technology. But the principle is there in the mathematics. Engineer the right pattern of entanglement, and you create a geometric bridge through spacetime. Even if macroscopic wormholes remain forever impractical, understanding the relationship between entanglement and geometry might enable other forms of quantum communication. In 2020, researchers proposed using emergent geometry in quantum systems to create quantum communication channels that are fundamentally more secure than conventional quantum cryptography. There's also the possibility of better simulation and prediction. If the universe operates on holographic principles, then we might be able to create computational models that leverage these principles to simulate physical systems more efficiently. Instead of tracking every particle in three-dimensional space, we could model the equivalent two-dimensional information pattern, achieving the same results with less computational overhead. This could revolutionize everything from weather prediction to drug design, from materials science to cosmological simulations. Understanding nature's own computational architecture might allow us to build our computers to operate on similar principles, achieving capabilities that current computational paradigms can't reach. Beyond practical applications, the holographic principle transforms how we understand our place in the cosmos. For millennia, humans have asked, "What is reality? What are we? How do we fit into the larger structure of existence?" Holographic cosmology offers new perspectives on these ancient questions. First, it suggests a deep relationship between mind and cosmos. If observation and information processing are fundamental to how reality manifests, then consciousness isn't separate from the physical universe, but integral to it. We're not external observers looking at objective reality. We're patterns within reality observing ourselves. The universe processes information, and at sufficient complexity, that information processing becomes conscious experience. Beyond practical applications, the holographic principle transforms how we understand our place in the cosmos. For millennia, humans have asked, "What is reality? What are we? How do we fit into the larger structure of existence?" Holographic cosmology offers new perspectives on these ancient questions. First, it suggests a deep relationship between mind and cosmos. If observation and information processing are fundamental to how reality manifests, then consciousness isn't separate from the physical universe, but integral to it. We're not external observers looking at objective reality. We're patterns within reality, observing ourselves. The universe processes information, and at sufficient complexity, that information processing becomes conscious experience. This doesn't make us special in a traditional sense. We're not separate from or above nature. But it does suggest our existence is less accidental than materialist philosophies suggest. In a holographic universe, observers aren't optional extras, but necessary features, patterns that enable information to organize itself into meaningful structure. Second, holography reveals unexpected unity in nature. Throughout history, physics has discovered unifications. Electricity and magnetism are unified in electromagnetism.
Space and time are unified in space-time. Mass and energy are unified by E equals mc squared. Holography represents perhaps the deepest unification yet. Information and geometry, the abstract and the physical, mind and matter, all unified as aspects of holographic information processing. This suggests that the apparent divisions we perceive between physical and mental, between information and matter, between observer and observed, might be artifacts of how we process information within the hologram, not features of reality's deepest structure. The universe is more unified, more coherent, more integrated than our limited perspectives suggest. Third, holography offers a perspective on meaning and purpose. In a purely materialist cosmos, meaning seems arbitrary, a story we tell ourselves to cope with a fundamentally meaningless universe. But if information is fundamental, if the universe processes information according to principles that generate complex, organized structures, then perhaps meaning isn't arbitrary, but emergent, something that arises naturally from how information organizes itself. This doesn't provide meaning handed down from above or embedded by external design. Rather, it suggests meaning emerges from within, from the patterns that information creates as it processes itself. We are meaning-making patterns within a meaning-generating cosmos. Our search for understanding, our creation of art and science and philosophy, our attempts to comprehend existence, all of this is the universe exploring its own structure, information examining itself. Fourth, holography raises profound questions about death and persistence. If all information is preserved on the holographic boundary, as the principle requires, then in some sense, everything that ever happened continues to exist in the complete boundary state. Your life, from beginning to end, is encoded permanently in the cosmic hologram. From the boundary perspective, you don't exist in time, experiencing moment by moment. You exist timelessly, your entire existence present simultaneously in the information pattern. This doesn't mean immortality in any conventional sense. Your subjective experience of time, of consciousness flowing from moment to moment, arises from how the hologram processes information in the emergent bulk. When your brain ceases functioning, that experiential flow ends. But the information pattern that constituted you, every thought, memory, and experience, persists in the boundary encoding. Whether this offers comfort or meaning depends on one's philosophical perspective. Some find solace in the idea that nothing is truly lost, that all information persists forever in nature's ultimate archive. Others see it as cold comfort, existence reduced to data points, consciousness to information processing, meaning to patterns in a vast cosmic computation. Recent breakthroughs suggest we're approaching a critical juncture in our understanding. The convergence of quantum information theory, gravitational physics, cosmology, and even neuroscience around holographic principles suggests we're circling something profound, some deep truth about nature that will transform not just physics, but our entire worldview. The next few decades might bring revelations that make current developments seem quaint in retrospect. The evidence accumulated over 50 years of research points consistently toward a conclusion that challenges our most basic assumptions. Reality is holographic. Information is fundamental. Space and time are emergent, and consciousness is an integral feature of how the cosmos processes itself. The holographic principle inevitably raises a question that's captured popular imagination. Are we living in a simulation?
If the universe is fundamentally information, if reality operates like a cosmic quantum computer processing data according to fixed algorithms, does that make our existence artificial, created by some external programmer? The question is older than modern physics. The philosopher René Descartes wondered if an evil demon might be deceiving him about reality. The ancient Chinese philosopher Zhuangzi dreamed he was a butterfly and woke wondering if he was a butterfly dreaming of being a man. The Vedic philosophers of ancient India proposed that the world is Maya, illusion, projected by deeper reality. But holographic cosmology offers a nuanced answer different from simple simulation. In the traditional simulation hypothesis, often attributed to philosopher Nick Bostrom, an advanced civilization creates a detailed computer simulation of reality, and we're characters in that simulation, running on some vast computer in a base reality external to our own. Holographic cosmology suggests something different. We're not a simulation created by external intelligence. Rather, the universe simulates itself. Reality is intrinsically computational, information processing itself according to fundamental laws, but there's no external programmer, no base reality beyond the holographic structure, no need for creators or designers. In 2019, physicist Sabine Hossenfelder at the Frankfurt Institute for Advanced Studies clarified this distinction in a widely cited paper. The universe being holographic, she wrote, doesn't mean we're in a simulation any more than the fact that reality obeys mathematical laws means mathematics is more real than physical stuff. The holographic boundary and the emergent bulk are both real, both aspects of the same cosmos. Neither is external to or more fundamental than the other. Yet questions remain. If our universe is holographic, could it be embedded in a higher dimensional space, like a hologram on a screen? The mathematics of ADS-CFT involves precisely this, a lower dimensional boundary theory and a higher dimensional bulk. Could our bulk universe be the boundary of an even higher dimensional space? String theory suggests this might be the case. In string theory, our universe has 10 or 11 dimensions, the 3 spatial dimensions we experience, plus time, plus 6 or 7 compact dimensions curled up at microscopic scales. Could these extra dimensions harbor realities we can't perceive, higher dimensional universes of which we're a holographic projection? In 2021, researchers at the Kavli Institute for Theoretical Physics explored this possibility through the lens of holographic cosmology. Their calculations suggested that our universe could indeed be a holographic boundary for a higher dimensional bulk, but with a twist. That higher dimensional bulk would itself be holographic, a boundary for an even higher dimensional space, creating an infinite tower of nested holographic universes. This isn't proof we're in a simulation, but it does suggest reality might be more layered than it appears, with our three-dimensional experience emerging from lower-dimensional information, while simultaneously serving as information for higher-dimensional structures. We're not in a simulation. We're part of a holographic tower where every level is both fundamental and emergent, both real and projected. The most profound implications emerge when we consider that the distinction between real and simulated might not be meaningful at the deepest level. If information is fundamental, if the laws of physics are algorithms processing that information, then calling the universe a simulation is just another way of saying it obeys consistent rules, which we already knew. The question isn't whether we're simulated, but whether that word captures anything meaningful about our existence. The holographic principle also transforms how we think about the multiverse, the hypothesis that our universe is just one of countless others.
Various forms of multiverse have been proposed: the many worlds interpretation of quantum mechanics, eternal inflation creating bubble universes, the landscape of string theory with its vast number of possible vacuum states. Holography connects to all of these while adding new perspectives. Start with quantum mechanics' many worlds interpretation. In this view, every quantum measurement causes the universe to split into multiple branches, each representing a different measurement outcome. You measure an electron's spin. It has 50% chance of being up or down. In the many worlds view, both outcomes occur, but in different branches. The universe constantly splits into parallel versions, exploring all quantum possibilities. Holographic cosmology offers a different picture. On the holographic boundary, there might be no splitting at all. The boundary state could encode all possible quantum outcomes simultaneously, not as separate universes, but as a single complex pattern containing all possibilities. What we experience as branching, as different outcomes in different worlds, might be how emergent bulk observers process a single boundary state containing superposed information. In 2020, physicist Sean Carroll proposed a holographic version of many worlds where the boundary encodes a vast quantum superposition of all possible universe histories. From the boundary perspective, all these histories coexist in a single quantum state. Only in the emergent bulk, only for observers embedded in space-time, do these histories appear separate. The multiverse isn't many universes. It's one boundary state generating many emergent descriptions. Eternal inflation presents a different multiverse scenario. In this model, the rapid expansion, called inflation, never completely ends. It stops in some regions, creating bubble universes like ours, but continues elsewhere, creating endless bubbles, each potentially with different physical properties, different constants of nature, different particles, different forces. Holographic cosmology suggests these bubble universes might all share a common holographic boundary. Each bubble would correspond to a different region or configuration of the boundary information, but all bubbles would be projections from the same underlying structure. The multiverse of eternal inflation would be unified holographically. Many universes in the emergent bulk, one boundary encoding them all.
String theory's landscape multiverse involves a vast number of possible vacuum states, each representing different ways the extra dimensions can be compactified, each giving rise to different physical laws. Estimates suggest 10 to the 500 or more possible vacua in the string landscape, an incomprehensibly large number of possible universes. Holographic duality suggests a remarkable possibility. All these string theory vacua might be different holographic descriptions of the same underlying structure. What appears as fundamentally different universes in the bulk might be different facets of a single boundary theory. The landscape wouldn't be separate universes, but different perspectives on a unified reality. In 2022, researchers led by Kamran Vafa at Harvard explored this idea through what they call the Swampland program, identifying which string theory vacua are consistent with quantum gravity and holography. Their work suggests most of the landscape might be swampland, mathematically possible but physically unrealizable configurations. Only a tiny fraction of possible vacua would correspond to actual holographic universes. This has profound implications. It suggests the apparent arbitrariness of physical constants and laws might not be arbitrary at all. The specific properties of our universe, the masses of particles, the strengths of forces, the number of dimensions we experience, might be largely determined by consistency requirements from holography and quantum gravity.
The universe is the way it is, not by chance, but because holographic principles constrain what's possible. The multiverse, in holographic perspective, transforms from an explanation for our universe's properties. We exist in this particular universe because only universes like this support observers, into a demonstration of how one underlying reality manifests in multiple ways. We might inhabit many universes simultaneously, depending on which level of description we consider fundamental. This forces us to reconsider fundamental assumptions about uniqueness and reality. Is there one universe or many? From a holographic perspective, the question might be ill-posed. There's one boundary, one fundamental information structure that generates multiple emergent descriptions we call universes. They're all real, all aspects of the same underlying holographic reality.
We've been discussing how space and time emerge from holographic information. But this raises a deeper question. What is the holographic boundary itself made of? If space and time aren't fundamental, what is? Current research suggests the answer involves quantum entanglement at the most basic level. Not particles, not fields, not even strings, but entanglement itself might be the fundamental building block of reality. In this view, often called it from qubit, reality is built from quantum information, specifically from patterns of quantum correlations that we call entanglement. Physicist Mark van Ramsdonk's 2010 breakthrough showed that space-time geometry emerges from entanglement structure. Remove entanglement and space tears apart. Add entanglement and geometry appears. This suggests entanglement is more fundamental than space, that the geometry we perceive is how highly entangled quantum information organizes itself. But what are the elementary units? What are the qubits in it from qubit? Several proposals exist. One involves twistors, abstract mathematical objects invented by Roger Penrose that encode both space-time position and momentum in a unified way. In twistor theory, the fundamental entities aren't points in space-time, but twistors in an abstract space, and space-time emerges from relations between twistors. Recent work by Nima Arkani Hamed and collaborators extends this idea through what they call the amplitahedron, a geometric object in an abstract space whose structure encodes particle interaction probabilities. The amplitahedron doesn't exist in space-time, rather, space-time emerges from the amplitahedron's geometry. Physics becomes an exercise in abstract geometry, where space-time is a derived concept. Another proposal comes from loop quantum gravity, an alternative approach to quantum gravity. In this framework, space is built from elementary units called spin networks, quantum states of geometry itself, like atoms of space. These spin networks evolve according to quantum rules, and their dynamics generate space-time. The holographic boundary would be a surface tiled with these elementary units of geometry.
Carlo Rovelli, one of loop quantum gravity's founders, has argued that time itself might not exist at the fundamental level. In his view, time is an approximate concept that emerges when we coarse-grain over microscopic details. At the most fundamental level, the universe is timeless, a quantum state with no temporal evolution. What we experience as time emerges from how we, as macroscopic systems, interact with and process information about the microscopic quantum state. A third approach involves causal sets, discrete structures where space-time points are replaced by events connected by causal relations. In this framework, fundamentally real are events and causal relationships. Space and time emerge statistically from large numbers of causally related events. The holographic boundary would be a causal set with specific structure that generates our observed spacetime when viewed macroscopically. All these approaches share a common theme. Spacetime is emergent, not fundamental. The truly basic entities exist in abstract spaces described by mathematics that doesn't presuppose space or time. What we call the holographic boundary might be a structure in one of these abstract spaces, and what we call the bulk universe might be an emergent property of that structure when viewed from within. This represents a radical break from the entire history of physics. Since Newton, physics has been formulated in space-time. We describe how things change in space over time. But if space and time aren't fundamental, we need a new language, new mathematics that doesn't presuppose space-time as background. Several research groups are developing such formulations. These approaches replace space-time with networks, with algebraic structures, with category theory, with amplitudes defined on abstract combinatorial objects. The mathematics is abstract and difficult, but progress continues. We're witnessing the birth of a new physics that will describe reality without assuming space and time as starting points. The most disturbing evidence comes from these explorations beyond space-time. At the deepest level, reality might be something we can barely imagine, something so alien to our evolved intuitions that we can only approach it through abstract mathematics. We evolved to understand mid-sized objects moving at moderate speeds, the physics of everyday life. We didn't evolve to understand the fundamental structure of existence. The fact that mathematics can take us there, that our minds can grasp these abstract structures even when we can't visualize them, is itself remarkable. We conclude where we began, with questions about the nature of reality and our place within it. The holographic principle, with all its mathematical sophistication and experimental implications, ultimately brings us back to ancient questions about consciousness, meaning, and existence. If reality is fundamentally information, what does that make consciousness? Neuroscience tells us consciousness arises from brain processes, neurons firing, chemicals flowing, electrical patterns propagating through neural networks. But from a holographic perspective, these brain processes are themselves patterns of information, emergent phenomena in the holographic bulk. Consciousness would be information processing itself in a particular way, creating subjective experience as an intrinsic feature of how information organizes at sufficient complexity. This isn't dualism, the idea that mind and matter are separate substances, nor is it pure materialism, the idea that consciousness is nothing but physical processes. Instead, it's a form of monism, where information is the fundamental substance, and both physical processes and conscious experiences are ways information manifests. Several physicists and philosophers have explored this idea through integrated information theory and its extensions. The key insight is that certain patterns of information processing create subjective experience not as a side effect, but as an intrinsic property of how the information is structured. Consciousness isn't something added to information processing, it is information processing of a specific type. In 2023, physicist Max Tegmark proposed that consciousness might be a particular state of matter, what he calls perceptronium, where information is integrated in ways that generate subjective experience. In holographic cosmology, perceptronium would emerge naturally wherever the information density and integration reach certain thresholds. Consciousness wouldn't be rare or special, it would be a common phase of information, like solid or liquid is a common phase of matter. This raises profound questions. If consciousness is information integration, and if the universe is fundamentally information, then at what level is the universe itself conscious? Is the holographic boundary conscious? Is the entire cosmos a vast integrated information system that experiences itself?
Most physicists resist this conclusion. The universe might process information, but that doesn't mean it has subjective experience as we understand it. Consciousness, they argue, requires specific types of information integration, feedback loops, internal models, integration of sensory information that don't exist in fundamental physics. Yet others are less certain. If information integration creates consciousness at one level, in human brains, why couldn't it create consciousness at other levels? Perhaps the cosmos has experiential properties we can't access, forms of awareness utterly alien to our own, but no less real. We might be localized islands of consciousness within a vaster ocean of experience permeating all reality. The question ultimately transcends physics and becomes philosophical, perhaps unanswerable. But what physics can tell us is this: the boundaries between mind and matter, between observer and observed, between information and physical reality, these boundaries are not as clear or absolute as they appear. Holographic cosmology reveals deep connections between concepts we thought were separate, suggesting reality is more unified, more coherent, more mysterious than our common-sense intuitions ever suggested. We are patterns of information complex enough to ask questions about our own existence, embedded in a holographic cosmos where space and time emerge from quantum entanglement, where consciousness and physics might be unified aspects of information processing itself. We're part of a universe that computes, that processes, that evolves toward ever greater complexity and integration. The journey from matter to life to consciousness to civilization might not be an unlikely accident, but an expression of the universe's fundamental nature, information organizing itself into forms capable of understanding information. In this view, science, our quest to understand reality, is the universe's way of exploring its own structure. Every equation we discover, every experiment we perform, every insight we gain is the cosmos examining itself through patterns of information we call human beings. We're not external observers studying an alien universe, we're the universe studying itself from within. This is the ultimate implication of holographic reality, the ancient mystical intuition that observer and observed are one, that consciousness and cosmos are unified, finds unexpected confirmation in modern physics's most sophisticated theories. Not through mysticism or faith, but through mathematics, observation, and rigorous theoretical reasoning, we've discovered that reality is fundamentally more unified, more mysterious, and more wonderful than we ever imagined. Black holes remain our most powerful laboratory for testing holographic ideas. Let's dive deeper into what happens when matter falls into a black hole and how holographic physics resolves the paradoxes. When an object crosses a black hole's event horizon, something remarkable happens from different perspectives. An outside observer sees the object slow down, redshift, and effectively freeze at the horizon, its image fading as photons stretch to infinite wavelength.
The object never appears to cross the horizon from the outside perspective. But for the falling object itself, nothing special happens at the horizon. It crosses smoothly and continues falling toward the central singularity. This is the equivalence principle. Locally, falling freely feels just like floating in empty space. The horizon is only special for distant observers, not for anyone crossing it. How can both perspectives be true? Holographic physics offers an answer. They're describing the same events using different information encodings. The outside observer uses the boundary description, where all information remains on the event horizon. The falling observer uses the bulk description, where the interior exists and can be traversed. Both descriptions are valid. They're holographically dual to each other. This resolves the firewall paradox mentioned earlier. The paradox arose from trying to combine both perspectives simultaneously, requiring the horizon to be both smooth for falling observers and information-preserving for outside observers. Holographic physics says you can't combine them that way. You must choose one perspective or the other, and each perspective is internally consistent. Recent work by Don Marolf and colleagues has explored this in detail through what they call holographic complementarity. The idea is that different observers have access to different but complementary descriptions of reality. No single observer can access both the boundary and bulk descriptions simultaneously. The information available to you depends on your position and history, your causal patch of spacetime.
This leads to a stunning conclusion. There's no single observer-independent reality in holographic theories. Instead, reality is perspectival, different for different observers, though constrained by consistency requirements, ensuring different perspectives don't contradict each other within their domains of validity. Black hole evaporation provides another testing ground. When a black hole emits Hawking radiation and shrinks, where does the information about infalling matter go? In holographic theories, it was never inside the black hole in the first place. It was always on the horizon, encoded in microscopic quantum degrees of freedom we call black hole microstates. String theory provides a microscopic description of these microstates. For certain types of black holes, string theorists can count exactly how many quantum states exist with given mass and charge. The count precisely matches the Bekenstein-Hawking entropy formula, further confirmation that holographic principles are correct. As the black hole evaporates, information gets transferred from horizon microstates to Hawking radiation. The process is unitary, information-preserving, in the boundary description. The apparent information loss in the bulk description is an artifact of using that description beyond its domain of validity. In 2019, Jeff Pennington, Stephen Shenker, Douglas Stanford, and Zhongbin Yang made a breakthrough calculating how information returns in Hawking radiation.
They showed that after the black hole evaporates past halfway, information starts coming out faster, encoded in subtle quantum correlations between radiation particles. By the time the black hole completely evaporates, all information has been recovered in the radiation. This calculation resolves Hawking's paradox definitively within holographic theories. Information is never destroyed, it's always conserved on the holographic boundary, even though it appears to be lost in the bulk description during black hole evaporation.
Our universe has a composition problem. Ordinary matter, atoms, molecules, everything made of protons, neutrons, and electrons comprises only about 5% of the universe's total energy density. The remaining 95% is divided between dark matter, about 27%, and dark energy, about 68%. Neither dark matter nor dark energy has been directly detected, but their gravitational effects are undeniable. Dark matter reveals itself through gravitational effects on visible matter. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more mass than we can account for with visible matter. Gravitational lensing, the bending of light by mass, shows more mass present than meets the eye. Something invisible exerts gravity, and we call it dark matter. Dark energy is even stranger. Observations of distant supernovae in the late 1990s revealed that the universe's expansion is accelerating. Some energy must be pushing space-time apart, working against gravity's attractive force. This is dark energy, and it's the dominant component of the cosmos. Holographic cosmology offers new perspectives on both mysteries. In standard cosmology, dark matter and dark energy are additional components we must add to make observations match theory. But in holographic cosmology, they might emerge naturally from the holographic structure itself. For dark matter, several researchers have proposed that what we interpret as dark matter is actually a manifestation of holographic effects. When we calculate gravitational fields in the emergent bulk spacetime, the holographic boundary contributes extra terms that look exactly like additional matter, dark matter, from the bulk perspective. In 2016, physicist Eric Verlinde at the University of Amsterdam published a controversial paper arguing that dark matter might not exist as particles, but rather as an emergent phenomenon in holographic cosmology. According to Verlinde's emergent gravity, when baryonic matter, ordinary matter, distributes itself in space, it creates a thermodynamic response in the holographic degrees of freedom, and this response manifests as what we interpret as dark matter. Verlinde's theory makes specific predictions that differ from standard dark matter models. In galaxy clusters, for instance, emergent gravity predicts slightly different mass distributions than particle dark matter would produce. Initial observations were mixed, with some supporting Verlinde's predictions and others favoring standard dark matter. The question remains open. Most physicists still favor particle dark matter, actual particles that interact gravitationally but not electromagnetically. Leading candidates include WIMPs, weakly interacting massive particles, or axions, hypothetical particles predicted by various extensions of the standard model. direct detection experiments continue searching for these particles in deep underground laboratories. Dark energy might also have holographic origins. The holographic principle places an upper bound on entropy in any region of space, and this bound is proportional to area, not volume. In our expanding universe, the boundary area is growing, allowing for increasing entropy. This increase might manifest as the accelerating expansion we attribute to dark energy. In 2018, researchers explored models where dark energy arises from the universe approaching maximum holographic entropy. As the cosmos expands and new spatial volume becomes available, the holographic boundary encodes information about this new volume. The energy required to encode this information appears in the bulk as dark energy, driving accelerated expansion. These holographic models of dark energy make predictions about how the expansion rate should change over cosmic time. Future observations with next-generation telescopes and supernovae surveys will test these predictions, potentially distinguishing holographic dark energy from other models like the cosmological constant or quintessence.
Why does time have a direction? Why do we remember the past but not the future? Why does entropy increase? These questions about time's arrow have deep connections to holographic cosmology. The standard answer involves entropy and the second law of thermodynamics. The universe began in a very low entropy state, highly ordered at the Big Bang. Since then, entropy has been increasing as the universe evolves toward more probable, more disordered states. This entropy increase gives time its direction. But this explanation raises questions. Why did the universe start with low entropy? A low entropy beginning seems incredibly improbable, requiring extremely special initial conditions. This is called the past hypothesis, the assumption that the universe began in an atypical low entropy state for no known reason. Holographic cosmology might solve this puzzle. In the holographic description, the beginning of the universe, the Big Bang, corresponds to a particular state on the holographic boundary. This boundary state might not be especially low entropy at all. The apparent low entropy of the early universe might be an artifact of how we describe that state in the emergent bulk picture. Think of it this way. The holographic boundary exists outside of time. It encodes all of cosmic history simultaneously, past, present, and future. The arrow of time, the flow from past to future, emerges only in the bulk description as a consequence of how holographic information organizes itself. From the boundary perspective, there's no past hypothesis problem because there's no time. The boundary state simply exists, and it generates an emergent bulk space-time where entropy increases. The arrow of time points in the direction of increasing entanglement complexity on the boundary, the direction where quantum correlations become more intricate. This connects to recent work on quantum complexity. Complexity is a measure of how difficult it is to prepare a quantum state or perform a quantum computation. In 2018, Leonard Susskind and collaborators showed that quantum complexity in holographic theories corresponds to volume in the emergent bulk spacetime. As the universe evolves forward in time, quantum complexity increases. Systems become more entangled, correlations become more intricate, and the state space required to describe everything grows. This complexity growth manifests in the bulk as expanding spatial volume and increasing entropy. Time flows in the direction of increasing complexity. This suggests a deep connection between computation, complexity, and cosmology. The universe isn't just evolving, it's computing. Each moment processes the previous moment's information, generating new patterns, new structures, new complexity. The arrow of time points in the direction of cosmic computation. Recent models explore whether this complexity growth has limits. In standard cosmology, if dark energy remains constant, the universe expands forever, cooling and diluting until nothing complex can exist, the heat death scenario. But in holographic cosmology, there might be constraints from information theory. The universe can't compute forever if it has finite information capacity. Some researchers propose that once the universe reaches maximum holographic complexity, once all possible information patterns have been explored, time itself might end or fundamentally change character. We're nowhere near this point. The universe has vast, unexplored complexity remaining. But in the unimaginably distant future, trillions of years hence, such limits might become relevant.
The holographic principle has intriguing implications for life and intelligence in the cosmos. If the universe is fundamentally information processing, then life, systems that store, process, and transmit information, might be less accidental than we think. The traditional view treats life as a happy accident. The universe's physical constants happen to allow chemistry. Chemistry happens to allow complex molecules. Complex molecules happen to allow self-replication. And self-replication happens to lead to evolution and, eventually, intelligence. Each step seems improbable, their combination extraordinarily so. The anthropic principle offers one explanation. We observe a life-permitting universe because only life-permitting universes can contain observers to do the observing. If the multiverse contains countless universes with different properties, we necessarily find ourselves in one where life is possible, no matter how rare such universes might be. But holographic cosmology suggests another perspective. If information processing is fundamental, if the universe is intrinsically computational, then life, sophisticated information processors, might be natural outcomes rather than accidents. The universe doesn't just permit information processing, it is information processing. Life emerges naturally in systems with sufficient complexity and energy flow. This connects to work on artificial life and complex systems. Researchers studying the origin of life have found that self-replicating systems emerge naturally in computer simulations with simple rules. Given energy sources, building blocks, and time, systems that copy themselves appear almost inevitably. Life isn't astronomically improbable, it's thermodynamically favored under the right conditions. In holographic cosmology, these insights take on deeper meaning. Self-replication is a form of information copying. Evolution is information processing with mutation and selection. Intelligence is sophisticated information integration. All the key features of life involve information, and if the universe is fundamentally informational, life becomes a natural expression of cosmic principles. This doesn't mean the universe is designed for life, or that life is inevitable everywhere. But it suggests that in regions where conditions permit complex information processing, like Earth's surface, with liquid water, organic chemistry, and stable energy sources, life-like phenomena should emerge naturally. The universe doesn't just accidentally permit life, it enables life through its informational nature. Intelligence takes this further. In integrated information theory, consciousness arises from specific patterns of information integration. Systems that process information in interconnected, causally effective ways generate subjective experience. Human brains do this, but so might other sufficiently complex systems. If the holographic principle is correct, and if consciousness correlates with integrated information, then intelligence might be widespread in the cosmos. Not necessarily biological intelligence, but any system that integrates information appropriately. Artificial intelligences, alien life forms based on different chemistry, perhaps even non-biological systems we wouldn't recognize as alive. The famous Fermi paradox asks, if intelligent life is common, where is everyone? We see no evidence of alien civilizations, no signals from the stars, no signs of galactic engineering projects. This seems to contradict the idea that intelligence emerges naturally. Holographic cosmology offers potential resolutions. One involves limits on information transmission. If space-time is fundamentally discrete at Planck scales, there might be bandwidth limits on interstellar communication that make detecting alien signals harder than we assumed. Advanced civilizations might use communication methods we don't recognize or can't detect. Another possibility involves observer selection effects. If we're holographic patterns experiencing one particular unfolding of the boundary state, other intelligences might exist in parallel branches or different regions of the holographic structure that we can't access. The multiverse might teem with intelligence, but holographic effects separate us into causally disconnected regions. A third option is that intelligence naturally leads to understanding holographic principles, and civilizations that grasp these principles might transition to forms of existence we can't detect. If consciousness is fundamentally informational, sufficiently advanced civilizations might upload themselves into pure information states, leaving the physical realm behind. These ideas remain speculative, but they illustrate how holographic cosmology transforms our thinking about life's prevalence and nature. We're not asking whether physics accidentally permits life, but rather how life expresses fundamental informational principles of cosmos itself. Understanding holographic principles could revolutionize computing. Current computers process information classically, with bits existing definitely as 0 or 1. Quantum computers use qubits that can be 0 and 1 simultaneously, enabling certain calculations exponentially faster than classical computers. But holographic quantum computers might operate on entirely different principles. Instead of processing information in three-dimensional space, they would process information on two-dimensional surfaces, using the same holographic encoding the universe employs. The advantage comes from error correction. Standard quantum computers are fragile. Environmental noise causes decoherence, destroying quantum information and causing computation errors. Enormous effort goes into error correction, encoding information redundantly so errors can be detected and fixed. This overhead dominates current quantum computer designs. Holographic quantum computers could use the natural error correction built into spacetime itself. The ADS-CFT correspondence is a quantum error-correcting code, as Daniel Harlow proved. Build a quantum computer that mimics this structure, and error correction becomes automatic, built into how the holographic surface encodes information. Several research groups are exploring this possibility.
In 2022, physicists at Caltech created a small holographic quantum error-correcting code using trapped ions, individual atoms manipulated with lasers. They encoded quantum information in patterns of entanglement that mimicked holographic boundary structure. The system automatically corrected certain errors without manual intervention. Scaling this to large quantum computers is challenging. Current prototypes use dozens of qubits. Practical quantum computers will need millions or billions. But the principle is proven. Holographic encoding can reduce error rates and simplify error correction. Another application involves computation itself. Some problems are naturally expressed in holographic language. Calculating quantum entanglement properties, simulating gravitational dynamics, modeling quantum field theories. These tasks might run more efficiently on holographic quantum computers than on conventional quantum or classical machines. This could revolutionize physics research. Many important calculations in quantum gravity, particle physics, and cosmology are currently intractable. The equations are too complex, the computational resources required too vast. Holographic quantum computers might make these calculations feasible, enabling simulations of black hole formation, early universe cosmology, or particle collisions at energies far beyond what accelerators can reach. Beyond physics, holographic principles might inform classical computing. Modern processors already face challenges from heat dissipation and quantum effects at small scales. As transistors shrink toward atomic scales, quantum uncertainty and heat generation limit further miniaturization. Holographic architecture might offer solutions. By organizing computation on surfaces rather than in volumes, by using natural error correction, by exploiting the informational structure that underlies reality, we might design computers that push past current limitations. Some researchers explore holographic memory, storage systems that encode information on surfaces with densities approaching the Bekenstein bound. Current storage media, hard drives, solid-state drives, store information in three-dimensional materials at densities far below theoretical limits. Holographic storage could reach those limits, storing vast amounts of data in tiny surface areas.
What happens to a holographic universe in the far future? Does holographic cosmology change predictions about cosmic destiny? Standard cosmology offers several scenarios depending on the universe's composition and geometry. If dark energy remains constant, if it's a cosmological constant, the universe expands forever, accelerating continuously. Galaxies beyond our local group recede past the cosmic horizon, disappearing from view. Stars exhaust their fuel and die. Black holes evaporate through Hawking radiation. Eventually, after many years, even black holes evaporate, leaving only a thin soup of elementary particles in cold, dark, ever-expanding space, the heat death. If dark energy weakens over time, expansion might slow, possibly reversing into contraction, the Big Crunch. The universe collapses back to a hot, dense state, perhaps rebounding in another Big Bang, creating an oscillating universe, cycling through expansions and contractions eternally. If dark energy strengthens, phantom energy, expansion accelerates catastrophically. Eventually, even atoms tear apart in a big rip, space-time itself shredding as expansion overwhelms all forces. Holographic cosmology adds new possibilities. If the universe has finite information capacity bounded by the Bekenstein bound, it can't expand indefinitely while maintaining complexity. At some point, the system reaches maximum entropy,
maximum information disorder, and nothing interesting can happen anymore. But holography also suggests the universe might be eternal in a different sense. On the holographic boundary, there's no time, just timeless information patterns. The entire history of the bulk universe, past, present, future, exists simultaneously as boundary state. From this perspective, the universe doesn't end, it's a complete, timeless structure. What changes is the emergent bulk description. At late times, after stars die and black holes evaporate, the bulk might lose geometric structure, becoming ill-defined or transitioning to some other phase. But the boundary persists, unchanged, encoding all of cosmic history, including its ending.
Some researchers explore cyclic cosmology in holographic context. Perhaps the boundary state describes multiple cycles, periods of expansion, contraction, and rebirth. Each cycle would appear as a separate universe from the bulk perspective, but all cycles would be encoded in a single boundary state. Another possibility involves transitions between different holographic phases. Just as water transitions between ice, liquid, and vapor, space-time might transition between phases with different properties. Our current expanding universe might be one phase, eventually transitioning to another where different physics applies. Physicist Sean Carroll and colleagues have explored baby universe scenarios, where quantum fluctuations create new regions of space-time that branch off from our own. These baby universes would be causally disconnected from ours, but part of the same holographic structure. The multiverse would grow fractally, with new universes continually budding from old ones. In holographic cosmology, these baby universes would correspond to different regions or excitations of the boundary. The boundary would encode a vast, branching structure of universes, each exploring different regions of the possibility space. There's also the question of whether consciousness survives cosmological timescales. If consciousness is information integration, and if information is preserved on holographic boundaries, then in some sense, consciousness persists as part of the permanent boundary state. Your experiences, thoughts, and memories are written into the cosmic hologram forever. This isn't personal survival in any conventional sense. Your subjective experience depends on dynamical brain processes that cease at death. But the pattern that was you, the information structure that constituted your mind, remains part of the universe's total information content, encoded permanently on the holographic boundary. Whether this offers comfort depends on personal perspective. Some find meaning in permanent informational existence. Others see it as cold abstraction, unrelated to lived experience. What's clear is that holographic cosmology transforms questions about endings and mortality, suggesting that nothing is truly lost, even if subjective experience is temporary. Holographic cosmology raises profound questions about personal identity. If you're fundamentally a pattern of information on a holographic boundary, what does that mean for continuity of self, for consciousness, for what makes you, you? Traditional philosophical views of identity involve either physical continuity, you're the same person because you're made of the same stuff or continuously connected stuff, Or psychological continuity. You are the same person because you have connected memories and personality traits. But holographic cosmology challenges both. Physical continuity fails because you're not fundamentally made of stuff. You're made of information. Your atoms are constantly replaced. Most cells in your body regenerate over time. What persists isn't matter, but pattern. And in holographic description, even the pattern exists not in three-dimensional space, but as encoding on two-dimensional boundary. Psychological continuity is more robust. Your memories, personality, thought patterns, these are information structures that persist even as physical substrate changes. In holographic description, these patterns exist as entanglement structures on the boundary, and their continuity through time creates your sense of persistent identity. But there's a twist. On the boundary, there's no time. Your entire life, birth to death, exists simultaneously as static information pattern. The experience of continuity, of being a self persisting through time, arises only in the emergent bulk description, only for observers embedded in emergent spacetime. From the boundary perspective, you aren't a process unfolding through time, but a complete, timeless structure. Past you, present you, future you, all exist simultaneously as different aspects of the same information pattern. The boundary encodes your entire history at once. This resembles the four-dimensional worm view of personal identity from philosophy of time. In this view, you're not a three-dimensional object moving through time, but a four-dimensional object extending through space-time, with temporal parts just as you have spatial parts. Holography adds another dimension to this, literally. You're a four-dimensional worm in emergent bulk space-time, and this four-dimensional structure is itself encoded on a lower dimensional boundary. Your identity is fundamentally informational, not material or even spatial. What about personal survival? If the boundary information persists eternally, does you survive death? In one sense, yes. The information pattern that constituted you remains part of the cosmic hologram forever. In another sense, no. Your subjective experience depends on dynamic processes that cease when your brain stops functioning. Some philosophers argue this distinction matters less than we think. If subjective experience arises from information processing, and if the boundary encodes all your experiences timelessly, then in some sense you're always experiencing your entire life simultaneously from the boundary perspective. The flow of time, the sense of present moment, emerges only in the bulk description. Others argue subjective experience requires genuine temporal flow, not just static information patterns. Experiencing requires processing, and processing requires change, and change requires time. Without time, there's no experience, just timeless information that could support experience if it were processed temporally. These debates aren't resolved and might not be resolvable, but holographic cosmology reframes them, showing that questions about identity and experience depend on which level of description we consider fundamental: boundary or bulk, information or experience, timeless pattern or temporal flow. We've explored how holographic principles explain space, time, matter, and even consciousness. But the deepest mystery remains. Why does anything exist at all? Why is there something rather than nothing? This is the fundamental question of metaphysics. Science explains how things work, how galaxies form, how stars burn, how life evolves, but not why reality exists in the first place. Even if we understood the holographic boundary completely, knew every detail of how it encodes bulk spacetime, we'd still face the question: why does the boundary exist? What brought it into being? Some argue the question is meaningless. Existence is brute fact. There's no deeper explanation. The universe exists, and asking why is like asking what's north of the North Pole. The question doesn't apply. Others appeal to God or necessary being, something that must exist by its own nature and creates everything else. But this just relocates the mystery. Why does necessary being exist? What makes it necessary? A third approach invokes infinity. Perhaps reality is infinite, an infinite multiverse containing all possible universes, all possible mathematical structures, all possible forms of existence. In an infinite reality, everything that can exist does exist, including us. No explanation is needed because everything is included by default. Holographic cosmology adds new perspective. Perhaps the question assumes wrongly that existence is a binary property. Things either exist or don't exist. But in holographic description, existence comes in levels. The boundary exists in one sense, the bulk exists in another. Neither is more real, they're different aspects of the same thing. Maybe existence itself is layered, with multiple levels of reality, each emerging from more fundamental levels, and perhaps no bottom level at all. Reality might be like an Escher painting, self-supporting, with no external foundation, each level emerging from and supporting other levels in self-consistent loop. Or perhaps, as some quantum cosmologists suggest, the universe exists because non-existence is unstable. In quantum mechanics, nothing means quantum vacuum, not absolute nothing, but state with minimum energy that still fluctuates. These fluctuations can create something from nothing, as quantum field theory demonstrates. Perhaps at the deepest level, absolute nothing is quantum mechanically impossible, and existence is inevitable. Physicist Alexander Vilenkin proposed the universe could tunnel from nothing into existence through quantum tunneling, the same process that lets particles pass through barriers. In his model, the universe's wave function has non-zero amplitude for beginning to exist, even from a state of nothing. The universe would be self-creating, brought into existence by quantum processes that don't require pre-existing time or space. In holographic context, this becomes even stranger. The boundary might be self-creating, a self-consistent information structure that generates itself. The boundary exists because it encodes its own existence. This sounds paradoxical, but mathematics contains self-referential structures, things defined in terms of themselves. Perhaps reality is the ultimate self-referential structure. Some physicists and philosophers argue we'll never answer why anything exists. The question might be forever beyond our grasp,
requiring perspective outside existence itself, which we can never have since we're inside existence. We can understand how reality works, but not why it is. Yet others argue the question will eventually yield to sufficiently powerful theory. If we discover reality's ultimate mathematical structure, the final theory physicists seek, that structure's properties might explain why it must exist. Just as certain mathematical truths are necessary, 2 plus 2 must equal 4, perhaps existence itself is necessary once we understand what existence fundamentally is. The holographic principle doesn't answer this ultimate question, but it transforms how we approach it. By revealing that reality is information, that space and time are emergent, that multiple descriptions of the same reality are possible, holography shows existence is stranger and more subtle than we imagined. The question, why something rather than nothing, might assume categories: thing versus nothing, existence versus non-existence, that don't apply at the deepest levels. Perhaps at the fundamental level, there is neither something nor nothing, but pure potentiality, pure information, pure mathematical structure that generates what we experience as existence. We are patterns in this structure, asking why we are patterns. Information, wondering why it's information. The question and questioner arise together, inseparable aspects of reality examining itself. What does it mean, practically and emotionally, to live knowing we might inhabit a holographic universe? Does it change how we should live, what we value, how we understand our place in reality? For some, holographic cosmology enhances wonder and appreciation. We're not just collections of atoms in empty space. We're intricate patterns in a cosmic information structure of incomprehensible sophistication. Every thought, every sensation, every moment of consciousness is the universe processing itself. Information examining information, reality experiencing reality. This perspective can be liberating. The sharp boundaries we perceive between self and other, between mind and world, between observer and observed, are artifacts of limited perspective. At deeper levels, everything connects. We're not isolated fragments, but nodes in vast network where everything influences everything else through quantum entanglement and information flow. For others, holographic cosmology feels cold or reductive. If we're just information, does that diminish us? If subjective experience is information processing, does that make it less real or meaningful? If space and time are illusions, what remains? But this reaction misses crucial point. Saying we're information doesn't make us less real. Information is fundamentally real. It's what reality is. And subjective experience, far from being diminished by information-theoretic description, becomes central to cosmic picture. Consciousness isn't accidental byproduct, but intrinsic feature of how information organizes itself. Living in holographic universe means recognizing that reality has depths beyond surface appearance. The solid table appears different under microscope. Atoms, mostly empty space. Atoms appear different in quantum description. Probability clouds. The quantum field appears different in holographic description. Information on boundary. Each level is real. Each reveals different aspects of the same underlying structure. It means recognizing that understanding and mystery deepen together.
The more we learn about holographic principles, the more we realize how much remains unknown. We've discovered space and time are emergent, but we don't fully understand what they emerge from. We've found connections between entanglement and geometry, but we don't fully grasp the underlying unity. We've glimpsed how consciousness might fit into informational cosmos, but hard questions remain. Living holographically means holding multiple perspectives simultaneously: bulk and boundary, emergent and fundamental, scientific and experiential, recognizing each as partial view of greater whole. It means accepting that ultimate truth might not fit cleanly into any single framework. Most importantly, it means recognizing our extraordinary position. We are patterns in the cosmic hologram that have become complex enough to study the hologram itself. Information organized so intricately it can understand information. We're participants in the universe's exploration of its own nature, not external observers, but internal processes through which cosmos examines itself. This should inspire both humility and boldness. Humility because we're tiny parts of incomprehensibly vast whole, our understanding limited by perspective and cognitive constraints. Boldness because despite limitations, we've grasped profound truths about reality's deepest structure. Creatures evolved to hunt and gather on African savanna have uncovered nature's holographic principles. That's extraordinary. Whatever comes next in our understanding, whether future discoveries confirm holographic cosmology or reveal something even stranger, the journey continues. The universe is vast, mysterious, and beautiful beyond imagination. The hologram contains depths we've barely begun to explore, and we're privileged to be here, now, in this moment of cosmic awakening, as reality investigates itself through minds like ours. We began with a paradox about black holes, a simple question about where information goes when matter falls into cosmic singularities. That question led us on a journey through the deepest mysteries of physics, the nature of space and time, the relationship between quantum mechanics and gravity, the fundamental structure of reality itself. The evidence we've accumulated points toward a revolutionary conclusion. Our universe is holographic. The three-dimensional space we inhabit, the time through which we move, the solid reality we touch and see, all of it emerges from information encoded on a distant two-dimensional boundary. Space and time are not fundamental features of reality, but emergent phenomena, cosmic projections from a lower dimensional screen we can never directly observe. This isn't speculation or science fiction. It's the logical consequence of decades of rigorous theoretical work and astronomical observation. From Hawking radiation to black hole entropy, from ADS-CFT correspondence to quantum entanglement, from the cosmic microwave background to gravitational wave astronomy, multiple independent lines of evidence converge on holographic principles as fundamental to nature. Yet we've learned something even more profound: the distinction between fundamental and emergent, between real and illusory, between information and matter, might not be as meaningful as we thought. The holographic boundary and the emergent bulk are both real, both necessary aspects of the same cosmos.
We are patterns of information experiencing ourselves as three-dimensional beings moving through time, and that experience is no less real for emerging from lower-dimensional encodings.
Current scientific consensus remains cautious but increasingly convinced. The holographic principle has proven too powerful, too mathematically rigorous, and too successful at solving long-standing problems to dismiss. Whether every detail of current holographic theories survives future scrutiny remains to be seen, but the core insight that information, geometry, and gravity are deeply connected in ways we're only beginning to understand seems secure. The universe continues to surprise us. Each answer generates new questions. What underlies the holographic boundary? How does consciousness fit into this informational cosmos? Are there realities beyond the ones we can access? The mysteries are endless, but we have tools now: mathematical frameworks, theoretical insights, experimental techniques that our predecessors lacked. We stand at a threshold. The next few decades will bring gravitational wave observations, quantum computer simulations, cosmological surveys, and theoretical breakthroughs that will either confirm holographic cosmology or point us toward something even stranger. Either way, we're witnesses to a transformation in human understanding as profound as the Copernican revolution or the quantum revolution. You are not simply an observer of this cosmic mystery. You are part of it, a pattern of information complex enough to contemplate its own existence, embedded in a holographic universe that processes itself toward ever greater complexity and self-understanding. Your consciousness, your thoughts, your search for meaning, all of this is the cosmos exploring its own nature. The universe is vast. The mysteries are endless. The journey continues. And perhaps most remarkably, we're here to witness it, to study it, to marvel at the extraordinary nature of existence itself. Reality is stranger, deeper, and more beautiful than we ever dared imagine. The hologram contains multitudes, and we are privileged to explore its infinite depths.